Here's a question. If I swap every 1 and every 4 in a Sudoku puzzle, does the solution change? No. The rules don't care which digit is which. They only care about relationships. So why do most neural networks have to learn that from scratch thousands of times over? That's the problem this paper fixes. So there's a family of compact neural architectures called Recurrent Reasoning Models or RRMs. No giant pre-training, no billions of parameters, just a small transformer block as you can see here, applied repeatedly, iteratively refining a solution like a human working through a puzzle step by step. Think of it as controlled, structured thinking in a loop. The catch? These models encode symbols, digits, colors with learned embeddings. Digit 1 gets one vector, digit 4 gets another completely separate. The model has no built-in knowledge that these symbols are interchangeable. So it compensates with massive data augmentation, shuffle the symbols, retrain on every permutation, which is expensive, inefficient, and it still doesn't fully generalize. So SE-RRM fixes this at the architectural level. The key insight is, instead of a 2D representation, features by positions, introduce a third dimension for symbols, as you can see here. So now your state tensor is features time positions time symbols. So every symbol gets the same embedding vector. A digit doesn't have an identity, it has a presence. At each position you get a 0 vector for every symbol that isn't there, and one shared learned vector for the symbol that is. Then the transformer block runs attention twice, one across positions, and so the model reasons about the spatial relationships, and once across the symbol dimension. So it reasons about which symbols are consistent with each other. These two attention passes interleave, and critically neither breaks the symmetry of the other, so as you can see here. So the formal guarantee is, if you permute the symbols in the input, the output permutes identically. This is equivariance baked into the weights themselves, not learned from data. So this is a deeper point than it sounds. Classic RRMs essentially fit a function that happens to be symmetric after seeing enough examples. SE-RRM is fitting within a hypothesis class that only contains symmetric functions. So you constrained the search space to exactly the solutions that respect the problem structure. And the consequence is generalization that vanilla RRMs simply cannot achieve. So the same principle applies to ARC-AGI, where colors are arbitrary labels. Swap red for blue, the solution logic is identical, and SE-RRM knows that inherently. This connects to a broader principle in geometric deep learning. The right inductive bias doesn't just improve performance, it changes what the model is capable by construction.